Here's a problem where limits are useful. So I have another function here. This function is f of x equals x squared minus 3x plus 2 over x squared minus 4. And once again, I'm going to ask, what is f of 2? Well, if we plug in 2, we're going to get 2 squared, which is 4, minus 3 times 2, so that's minus 6, so that's negative 2, and then plus 2, so that's 0. Okay, so it's 0 on the top there. And then we have 2 squared, so that's 4 minus 4. Oh, 0 on the bottom. We got 0 over 0. And of course, anytime you have division by 0, you have a fraction with 0 on the bottom. In math, this is undefined. This function has no value at this point. Now, just for fun, over here on Desmos, I've actually graphed this function. And if you look here, you'll see that if I bring my mouse here and I grab a point and I move it over to where x is 2, you'll see the solid dot there suddenly becomes hollow. And there it is, it's undefined, right? So, in fact, this function has no value at 2. But this thing we found 0 over 0 is sometimes called an indeterminate value. And when you see something like this, we might ask the question, well, can the limit shine any light on this? Because as we can see, the graph appears to be going towards a point. It may not actually be defined at that point, but maybe the limit can help us figure out where that point might be. So I'm going to try to take the limit as x approaches 2 of this function x squared minus 3x plus 2 over x squared minus 4. Well, what's the first thing I'm going to do? I'm going to factor the expression on the top and on the bottom. So that gives me x minus 2 and x minus 1 on the top, and on the bottom, if you know your difference of squares, x minus 2 and x plus 2. And then seeing that, I noticed there's a term in common, x minus 2 on the top and on the bottom, so we can cancel those out, and that gives us the limit as x approaches 2 of x minus 1 over x plus 2. And then, well, if I were to plug 2 into that, that would give me 2 minus 1 over 2 plus 2. That would give me 1 over 4. And so we would say that the limit as x approaches 2 of our function is 1/4. Now, if we go back to our graph on Desmos, what you're going to see is that the y values, if you look carefully, as we get closer to 2, we got 2.3, 0.23, 0.24, 0.246. Looks like that point is actually at a y value of 1/4. So what we've done by finding this limit is essentially we found a point that doesn't exist. We find the point the function is going towards but never reaches. Now, that's fine. So useful to us, that point, that what we would call a hole in the function, is at 2 1/4, okay, on our graph. But there's something that might occur to you after a little while. You might look at this and say, well, I get all this, and this is wonderful, but you know, if I took this thing we just did and I were to cancel out this limit as x approaches 2 we wrote at the beginning of each line, couldn't we just do everything we did? I mean, what did we do? We factored, we canceled out some terms in common, and then we plugged in 2. Did we really need to write that limit thing? I mean, was there anything in there that without writing the limit, we wouldn't be able to do? And the answer is actually yes. In the second step there, I canceled out the x minus 2 on the top and the bottom that were in common. You can't actually do that. Why can't you do that? Well, because that's what's making the function be 0 over 0 when x is 2. If you remove that, you've just changed it to a different function. Well, you can't just randomly change something for no reason. Now, you might say to me, well, Michael, but I remember in grade 11, I think it was, we did these things where we had all these fractions and we factored the top and we factored the bottom and then we canceled out all these things in common. You did do that. But if you were taught this correctly, there was something your teacher always made you do first. If you remember what that was stating your restrictions, your non-permitted values. Right? At the beginning, before you do that, you'd say, well, look, I'm going to start by saying x can't equal 2, and then I can cancel this out, right? Because the whole point is it's at 2 that this problem occurs. So stating restrictions is what allows you to be able to simplify those terms from the top and the bottom and cancel them out. Well, did we state restrictions here? Well, no, we didn't. But if you'll remember from the other video, what's the one point that we never reached when we took the limit as x approaches 2? The answer is the one point we never reached was 2. So stating the limit at the beginning of each row is kind of like stating restrictions. We're saying, well, hang on a second, x is approaching 2, but it's never actually going to be 2. And because it's never going to be 2, then x minus 2 on the top and on the bottom, those are just two numbers that have the same value, so we can cancel them out. If x never reaches 2, well, they'll never be 0, so then it's not a problem. Okay then, but the next thing you'll tell me is, well, Michael, you went ahead and after saying x is never going to equal 2, you plugged in 2. You're a liar. Well, no, I'm not. Well, kind of, but okay, let me explain. I didn't actually plug in 2. Well, I kind of did, but here it is. See, when I plug in 2 in that last line, what I'm plugging in is 2.000000000, infinite number of zeros, 1. I'm plugging in a number that's not 2, but is infinitely close to 2. Well, actually, I did plug in 2. I did plug in 2, but the reason I plugged in 2 is not to find out what's happening at 2, but because by plugging in 2, I'm finding out the value that when I plug in a number infinitely close to 2, that's the value I would be infinitely close to. In other words, I'm not plugging in 2 to find out what the function is at 2, but to find out what it's approaching as it gets close to 2. And that allows me to plug the number in. So this is the great genius, philosophically, of limits. They allow us to do this little sidestep where we say, well, over here, we can cancel out these terms because we're not actually going to get to 2, but then we can plug into 2, but not because we're actually finding out what's happening at 2, because we know what happens there, the function doesn't exist, but because we're trying to see what it's approaching. And because we do this, this allows us to take the limit and get a value. Now, do we pay a price for this? Of course, you always do in math. The price we pay is we haven't found out what's happening at 2. We already know the function's undefined. This is not the value of the function, but it does tell us what the behavior of the function is around that value. And that's something useful for us to know. In the next value, I'm going to show you somewhere where this actually gives us something incredibly useful in a real sense. Now, in the next video, I'm going to show you a situation where limits actually give us something that is of incredible use. Check out my next video on using limits to find derivatives to see a really important example of where limits are incredibly useful. And if you're wondering what limits are, check out my Introduction to Limits video as well.